Hello, all. My name is Sudhindra Gopal Krishna, and today I'll be presenting my work on factorizing million scale non negative matrices using compressed structure. I'd like to first thank IARIA and All Data for providing me another opportunity to publish my work. So let's get on with my introduction first. I'm a final year PhD candidate at the School of Computer Science and University of Oklahoma, and my research focuses on democratizing resources to research via storage, storing the data in a smaller footprint, and performing the required operation on the stored data. So here we do not, my research focuses on using the stored data without having to extract them completely. And I'm originally from Bangalore, India, where I received my bachelor's degree and moved to United States for my master's and PhD. Apart from my work, I also teach here at OU, and I'm also engaged in a lot of outreaches, which focuses on helping the students, the high school students, and the teachers in rural parts of Oklahoma to access materials for computer science. Coming on to today's work, the contents for today's presentation goes this way. So I'll do some introduction with respect to matrix factorization and several matrix operations. Then I'll see the background on how the matrix factorization has evolved over time, and some of the matrix operations that are involved in this factorization, which is performed on the compressed data structure. And we propose our methodology to perform the matrix factorization, the heuristic approach for improving the factorization. Then we'll go to evaluation of our methodologies and concluding it by our conclusion and future work. So when it comes to matrix factorization, the first thing springs to mind is separating two matrices or decomposing the matrix into multiple matrices in order to extract information. So the information could be reduction of features, removal of unwanted features within the matrices. So what are some of the applications, or where in which field are these matrix factorizations used? So we use matrix factorization in the area of mathematics and computer science, perform linear algebra, signal processing, and machine learning. So few of the matrix factorization methods that are heavily used are single value decomposition and principal component analysis in the field of machine learning, and non-negative matrix factorization when it comes to machine learning as well, but in terms of data compression, or in terms of text data mining and so on. The application, as I spoke earlier, are on image and video processing, collaborative filtering, data compression, and so on. So for this paper, we will mainly focus on using non-negative matrix factorization, and how do we process the non-negative matrix factorization using our compressed structure. So a non-negative matrix factorization is a type of matrix factorization where matrices are constructed constrained to contain only non-negative values. So non-negative values are values that are greater than or equal to zero, and there are certain matrix factorization method that do just values above one. So those are positive matrix factorization and regular matrix factorization that do allow negative values. But in this case, we will just stick to values that are that do not contain any negative values. NMF is often used as a tool of dimensionality reduction, feature extraction. So whenever we have a machine learning data and we want to extract features, those are the column names for the machine learning algorithm. NMF is often performed, and it produces interpretable and sparse data representation. Some of the most common applications of NMF are topic modeling, image and video processing, and text mining. And text mining, for example, is getting the document frequency. So we do TF-IDF to extract all the words that are important within the text document by eliminating the stop words and other words which do not contribute to the importance of that particular document. So matrix factorization, especially NMF, is used in such application. So as you can see here in this figure, we have a matrix A, and matrix A has n number of rows and m number of columns, and it is approximately divided into two matrices W and H, and the W and H are of dimension n cross k and k cross m. So k is called the rank of the matrix. By definition, or by the property of NMF, we usually have a lower k for a better compression or better data representation. But finding k or finding rank is one of the problems, or one of the problem on its own, for performing an optimal NMF. So what are the constraints with respect to performing an NMF? So NMF is, as I said, as we saw in the previous picture, it's about dividing it into two matrices W and H. W is a matrix of size n cross k, where n is the number of rows and k is the rank of the factorization, and matrix H, which is of size k cross m, where again m is the number of columns and k is the inner rank of the matrix. And W and H both are non-negative matrices with all the entries greater than or equal to 0. So once you divide the matrix, how do we know that the resultant matrix? So we say that A is equal to W times H, correct? So how do we process that? Okay, how off is the W times H compared to the matrix A? So to do that, they perform Frobenius norm. So Frobenius norm gives you the distance between two matrices, that is the total number of differences in two matrices. So to perform a Frobenius norm on the NMF, so we subtract the matrix A with the multiplied matrix W and H, and we take the absolute squares of these numbers, and we get to know if we are too far off the original matrix, or are we at the optimal distance. So let us look at different NMF algorithms that are proposed by different authors over few decades. Some of the sequential algorithms that perform NMF are multiplicative update algorithm, which was one of the first algorithms to be proposed. Later on, followed by gradient descent algorithm and alternating least square. In this paper, we will evaluate the multiplicative update algorithm. As we said, it's one of the first algorithms to be proposed by Lee and Seung in non-negative matrix factorization. So multiplicative update algorithm is as follows. So iterative. So W and H are two random matrices. Initially, we consider W and H are two random matrices. These random matrices are of rank m cross k and k cross n, as we spoke earlier, and we perform the iteration by multiplying several matrices together and transform of a matrix and so on. Here we represent the original matrix. So W transpose times V times W transpose times W times H. So the whole thing is denominator, and the H is again divided by this denominator. So this is an element-wise division. So when do we stop performing this operation iteratively? So H and W are updated every iteration. So when do we stop? So when the Frobenius norm tends to be very low, or two Frobenius norm is not getting updated no matter how many iterations you perform. So you perform these operations again and again to obtain an optimal W and H. As you can see here, the total number of operations needed to perform one iteration is massive. So we have one element-wise multiplication, we have matrix multiplication here, so, and we have an element-wise division, three matrix multiplication, and element-wise addition to avoid non-negative negative values, and you do the same number of operations for W as well. So we have about 12 operations to be performed for one single iterations. And mind it, we are performing on the matrices, and matrices are known to consume a lot of space when we are operating on a regular system. It becomes a little challenging. So, what are some of the disadvantages that people have seen with respect to the multiplicative update algorithm proposed by Lee and Sung? So a local optima is one of the disadvantage. The iterative procedure proposed can sometimes converge to a local optima rather than a global optima, which gives you a lot of noise with respect to W and H. The initialization of W and H is really important, as we saw earlier in the algorithm. So the initialization of W and H are random values. So what random values are you going to initialize them? Is it going to be all ones, or how many zeros are you going to include? So that is one of the disadvantage, that you do not know how sensitive the data could be. Then overfitting could be one of the disadvantage here. So you have the inner rank, correct? So coming up with a good inner rank, which is k itself, is an NP hard problem. So you have to perform. There are a lot of algorithms that have gone through getting an optimal k for a given data. And the base matrix obtained by NMF can be difficult to interpret, particularly if the rank is chosen really high. If the rank is chosen high, you're basically defeating the purpose of dividing it into two matrices, and basically you're creating two larger matrices again. You're not really reducing the features or dimensionality when you want to perform matrix factorization. Last but not least, we have a problem of memory here. So since these are 2D matrices with values, we know that matrices tend to consume n times m times the log of integers or values, whatever it is, so 64 bits. So it blows up even for a smaller matrices. So how do we solve some of these problems by still keeping multiplicative update in our mind? So one solution for the storage that we propose here is to use the compressed structures. In this paper, we are going to make use of the novel compression technique, which is compressed binary tree, and already existing compression technique, which is compressed sparse row. Compressed sparse row is one of the widely known, well-known storage mechanism, and compressed binary trees are in-house storage mechanism, which helps in performing all these operations while the data still being compressed. So in this paper, we solve the problem of memory requirement. We compress all the matrices A, W, and H. All matrix operations required to obtain W and H are all performed by partially deflating the data. So we do not create an intermediate structure where we convert our compressed data structure to this intermediate data structure and perform operation. So we are basically defeating the purpose of compressing it in the first place if we are deflating the data uh, entirely. So let us see what are the steps that we can take in order to perform the operations that we mentioned earlier, where we had about 12 operations, which were element-wise matrix multiplication, element-wise matrix division, multiple matrix multiplication, matrix transpose, and matrix subtraction to perform Frobenius norm, whilst keeping the data compressed. Okay. So before we move on to the actual algorithm, I'd like to give you some background on the already existing matrix factorization techniques that were proposed. So in 1994, Pietro and Tapper first coined the matrix factorization with the positive matrix factorization. Then Lee and Sung got inspired by the work that Pietro and Tapper proposed on positive matrix factorization, and they came up with the non-negative matrix factorization. seeing the value of the non-negative matrix factorization, Gonzalez and Zhang proposed an alternative to multiplicative update algorithm because the disadvantages were a lot, but they weren't successful in obtaining a better convergence or a better rank. They still ended up having the same complexity as Li and Sun. And Lin in 2007 came up with improvised convergence, but at the cost of increasing the number of operations required to obtain the same W and H. So they have always seen these trade-off between the convergence and the storage or number of operations that are performed on the matrix. So a positive matrix factorization again was coined by Pietro and Tapper in 1994. It's just that all the factors are positive and not non-negative. So Li and Sung got inspired by this work. So alternatives to Li and Sung were by Gonzalez and Zhang. Again, as I said, did not get much of a traction because they still had that convergence problem. But Lin tried to solve it, but with the cost of more operations per iteration. So the efficient storage techniques that I spoke about earlier are all already proposed and published in previous work. So since these are all sparse matrices, sparse matrix do contain a lot of zeros in them, which is expensive and redundant. So the sparsity of the matrix is defined as number of non-zero elements to the number of possible elements that could be present in a matrix. So lower the number of non-zero elements, that means the matrix is a lot sparser. And our algorithms, CBT, and already existing structure CSR work efficiently with respect to storing large sparse data. But one of the disadvantages of CSR is you cannot stream stream new values into the already existing structure because you have to resize the arrays that are present in the CSR, and then we have to store the new values. Whereas in compressed binary tree, as and when the new value is coming in, you can stream the new value into the structure and delete the already existing value without having to decompress a lot. And this goes when you are updating W and H again and again. So you can update on the same W and H compressed structure instead of rewriting W and H again and again, as you have to do with CSR. So coming up to the matrix factorization, matrix operations that have to be performed on for factorizing the two matrices. We saw that we have multiple matrix multiplication. So you saw that we had W transpose times W times H, which is three matrices getting multiplied. Traditionally, when you multiply three matrices, so you multiply two matrices at once, and the resultant of these two multiplication is multiplied with the third matrix to obtain the resultant. So we are going to show a technique using a structure where you can multiply three matrix at a time. So you're taking a row of matrix A and multiplying with a row of matrix B, are multiplying with matrix B and multiplying with matrix C to obtain the row of matrix D. So performing this iteratively, you can actually come up with the resultant matrix D with just n cubed number of operations instead of doing n cubed times n cubed number of operations. Then we have element-wise matrix operations such as multiplication, addition, division, and subtraction. And all of these are again used within the algorithm itself to come up with W and H. And last but not least, we have matrix transpose. So we had W transpose times W. So when it comes to matrix transpose, you have to create another matrix, correct? So the matrix you're transposing should be stored somewhere. So that again constitutes to storage, which is expensive in our case. So we are trying to reduce the storage as much as possible to perform any operation. So we have proposed a technique to access the elements of the matrix in a transposed manner when you see it as a resultant. So we have proposed both A transpose times B and B transpose, A times B transpose to obtain the final result without having to create a new structure again. So let us look at all the element-wise operations, algorithms to perform the element-wise operation. Note that here I have mentioned the input of these operations as matrix A and matrix B, but since for the simplicity's sake, I've just kept it matrix A and B. But in reality, those are compressed structures. So it's compressed matrix A and compressed matrix B. So it could be CSR or it could be CBT, and the operation that you would like to perform on these two matrices, it's either multiplication, or if it's either multiplication, division, addition, or subtraction. So um, one of the basic conditions for all these element-wise operations are both the matrix should be of same size. So if they are not of same size, then we say you cannot perform the operation. It's just a check that you'd like to have when you're presenting these algorithm to the public. And it's very simple that we iterate over all the rows of one matrix and do the necessary operation that you want it to perform on one row at a time. So here, if a row of A is 0 and if the row of B is 0, we know that the resultant row is 0 no matter what operations we are performing. If the row of A is 0, if you are multiplying or if you're dividing, then the row of B is 0. Or if you're doing addition, that means that you are just copying the other row of the matrix into into the resultant matrix. And finally, if both the rows are non-zero, you perform the operations that you were thinking of, and you get the resultant row of C, and we perform on all the rows of the matrix to obtain the resultant matrix. So this was one algorithm, and with few more conditions to eliminate multiplying two matrices where both the matrices are each one of the matrix is zeros, and then the entire row is zero. And division, we take care of dividing by zero error as well, because uh, you only perform this operation if both the elements are non-zero. So thereby eliminating the need for performing the divide by zero error. Next, oh sorry. Um, Next, we have matrix transpose. So as I said, we proposed a technique, in fact, two techniques to multiply a transpose and a regular matrix, and a matrix and a transpose of that transpose of the other matrix. Since coming to A times B transpose, we know that multiplying a row of matrix A, and multiplying the column of matrix B gives you the partial sum of a row of matrix C in our case. So multiplying this and multiplying this on a transposed scale will actually give you the column instead of giving you the row of matrix C. So the the acronym for B transpose is shown, but the actual matrix is not transposed. So you perform the regular matrix operation, and you obtain the result of the matrix without having to transpose. Similarly, with A transpose B, since you are multiplying a row of matrix A and a column of matrix B, what you actually had to be doing was multiply the column of matrix A and the column of matrix B. So if you see the access pattern, to store the transpose, instead of storing the result row wise, you store the result diagonals. So you store the result as diagonals, as shown in the different colors here, and this gives you the A transpose times B without having to transpose the actual matrix. So this was also an in-place technique, no intermediate data structures being used to perform these matrix multiplication. Um, the matrix multiplication is also been published in our paper, in our previous paper, the work of multiplying two matrices even when they are compressed using partial sum matrix multiplication. Then we have our third methodology, which is multiple matrix multiplication. In this figure, we see that we are using a row of matrix A, uh, entire matrix B, and an entire matrix C. So, and we are trying to obtain the row of matrix D. Here we are showing an example of A times B times C, but in reality, this could be A times B times C times D times E times F times. So you can have multiple matrices, and our algorithm would still work given any number of matrix to multiply. You can multiply it in one single go instead of doing it again and again and again by storing the intermediate data structure. The performance of this was actually seen very evidently when we considered a million by million matrix with varying sparsity. So each one of the red dots or each one of the data point is of various sparsity, and the time required to multiply our time required for the traditional multiplication against the sequential matrix multiplication. And we see that our sequential matrix multiplication, that is multiplying all the matrices at once, yielded a lower time compared to our actual our traditional multiplication, where you're also storing the matrix. Here we are just showing you the time required to multiply these two matrices, but we also have to include also remember that the storage required to store it using the traditional way, where you're storing the intermediate matrix, is quite larger compared to the sequential matrix multiplication. So once we establish all these matrix multiplication and matrix operations, all we had left was to perform the matrix factorization. But we also wanted to introduce some of the heuristics for faster convergence. As we saw, faster convergence was one of the disadvantages, or slower convergence was one of the disadvantages of multiplicative update algorithm. So to induce a faster convergence, one has to tweak the input matrix itself. So having more zeros means you are actually getting an optimal matrix on an earlier stage. So how do we eliminate these? How do we tweak the input matrix? It could be one of the question. So we would set a threshold such a way that we parse one row at a time, and if the row doesn't lead to a good, if it is not of any use, if it is not leading to a drastic reduction in our optimality, then we say that the row is of no use, so we can make the entire row zero. So here, making that entire row zero, meaning we are eliminating the noise in the data, because a row which does not constitute to any result means that it is basically noise. So we are doing two things here. We are compressing the data. We are even more compressing the data structure by eliminating the non-zero elements, and we are removing the noise in the input data. So of course, the heuristic will not be very optimal compared to the having the matrix as is, but it's going to still give you a better result, faster convergence when compared to doing the traditional matrix factorization. So we propose this heuristic, and with that, let us see some evaluations that we performed on both CBT and CSR. So our input matrix was of size 55 MB for the smaller matrix, and the largest matrix was of size 32 gigabytes. When we store that in our compressed structure, we see that there was a drastic reduction with respect to in CBT and CSR. And when you compute W times H, you get a closer estimate of these values. So we were able to get close enough non-zero elements with the Frobenius norm, and we chose these inner ranks randomly. So we went through iterations after iterations to find which inner rank produced a better Frobenius norm, and that's how we operated on. And again, there is a whole lot of research that goes on to finding an optimal inner rank, which we are not going through in this paper. We are only concerned about how can we improve the space complexity of factorizing two matrices using factorizing a matrix using multiplicative update algorithm. And here we can see that average memory per iteration. So if you are considering matrix, then the average memory that per iteration you require about 32.64 gigabytes for a largest data, that is computing W and H again and again and again. So what would be the average memory iteration per iteration, and what would be the average memory iteration when you consider doing CPT and CSR? So this gives you an idea as to why we would need compressed structures to perform this factorization algorithm. So for us, this is relatively a smaller matrix, which is 65,536 by 65,536, is relatively a smaller matrix when compared to the real world data, which is about a billion rows and billion columns. Imagine the blow up of the storage required to store the storage for a matrix. It would be in terabytes. And thinking about terabytes, having any system having terabytes is something unknown for a regular user. So having our compressed structure to perform these operations gives you a better result in performing the factorization. Lastly, here is a graph of the convergence of W and H per iteration. And we would stop at a point where we saw we had optimal number of W and H, and we also had optimal Frobenius norm. This is just a graph to show that the initial matrix that we consider in the iteration 0 is way off. So how the algorithm converges is one of the good questions that would be asked going ahead. So in conclusion, we perform million scale matrix factorization directly on the compressed structure. Intermediate results can be eliminated using multiple matrix operations that we saw earlier. We introduced element-wise matrix multiplication, division, subtraction, and addition, and sequential matrix multiplication, which we had never done in our previous papers before. And we introduced traversing of the matrix in a pattern to perform matrix transpose without having to transpose the entire matrix. We also proposed a heuristic relationship between inner rank and sparsity of the sparsity factor of the matrix. Lower rank leads to smaller factor, but need not be an optimal, or a higher rank leads to larger memory consumption, which is also not good. So finding an optimal is always a way to go for W and H. In the future, we would like to expand our compression technique on ALS, which is alternating least square, GD, which is a gradient descent, and binary matrix factorization or Boolean matrix factorization on the compressed algorithms. And with that, the floor is open for questions, and thank you for your time.